we're on the record.
Great. So welcome everybody to our weekly colloquium, and this will be the final colloquium of this semester. So today we're very happy to have Janet Conrad. So Janet is a Ohio native. She's from Worcester, not too far from here. So Janet got her PhD at Harvard University and did a postdoc at Columbia University, and then was hired on as a professor at Columbia University in 1999, where she proceeded to win all of the major early career awards like the NSF Career and the Presidential Early Career Award and the Sloan Fellowship. And then in 2008, she moved to MIT, where she is now, and continued to win prestigious awards such as the Guggenheim Fellow. And for many years, she's really been at the forefront of the field of experimental neutrino physics, being a part of most of the major experiments in that area. So we're very fortunate to have her here today to tell us about elephants and oscillations. Take it away.
Okay, let me just reduce the thumbnail. Okay, and put this full screen. So this should now be full screen. Are you all seeing that?
Yeah.
Okay, and I want to say I can't actually see you. So I've asked Harsh, if somebody raises their hand, he should go ahead and call on you, and you should, but the simplest thing will be for you to just speak up. So please feel free during this talk to just speak up and talk to me. I'll be very glad to do that. And yeah, I'm going to tell you about elephants and oscillations. It's a title that gets people to come to the colloquium. So this talk is actually about neutrinos. And these are the lightest of all the fundamental spin 1/2 particles. And in our standard model, neutrinos are massless, although Ben Monreal is working hard to try to show you directly what the neutrino mass is. And this has been a hard job for him because now experiments are showing that they do have mass, but they have very, very tiny masses. And having found that neutrinos have mass was a really big surprise. And I'm a great believer in looking under the lamppost. If you've discovered one thing that's a big surprise about the particle, you should look because there could be other big surprises there. And so this talk is going to be about the neutrinos that we know about, why we think there may be other kinds of neutrinos, and a decisive way to search for new neutrinos. So let me begin by just reminding you a little bit about neutrinos, because many of you probably don't think about them all the time, although actually 40 billion neutrinos are going through your thumbnail right now. They're coming mostly from the sun here on Earth. They're coming from other places also, though. There's actually about 10 to the 9 per cubic meter just coming from the Big Bang. There's neutrinos that come from supernova. There are neutrinos that come from cosmic ray showers. Also, there are human-made neutrinos, beams from reactors, and also from particle accelerators. And the reason why you don't realize that these are going through you is because they interact by the weak force. And these interactions don't happen very often. Weak is aptly named. So if I want to compare for similar energies of incoming particles, solar neutrinos, the cross-section is going to be 10 to the minus 43 centimeters squared, compared to a similar center of mass energy for proton-proton collisions, where the cross-section is 10 to the minus 24 centimeters squared. So there's nearly 20 orders of magnitude difference in this. And that is why it is that we say that neutrinos have a very weak interaction. So a neutrino of those energies has a good chance of traveling through 200 Earths before interacting at all. And we're going to describe neutrino interactions in terms of exchange particles. And I'm sure you're all familiar with this, but I just want to remind you, I'll describe it in terms of the Feynman diagram. So time goes along the x-axis, position along the y-axis. Your neutrino is coming in and it interacts with, for example, a d quark by way of exchange of a particle. It's the Z boson, and the Z boson doesn't carry any charge. So the neutrino comes in, this neutral particle is exchanged, hitting the D, and the neutrino goes out. It's your classic elastic interaction. However, the weak interaction also has an electrically charged counterpart. It has an exchange particle called the W. So you could think of it this way. The neutrino comes in, exchanges a W plus that hits the D, and that has to turn this into a U quark because it has to absorb the positive charge. And out comes a particle with -1 charge in order to be able to maintain the overall net charge. This is called the charge current interaction. And I want you to remember that word and what I mean by it, because I'm going to use it. It's a buzzword and I'm sorry about it, but it pops out of my mouth. So I just wanted to flag it as a word you should be sure to remember, which is just that the case where the neutrino comes in and a charged particle comes out is the charge current interaction. So in the simplest of models, the W boson is actually flipping particles within what we call weak doublets. So in other words, if you have a muon type neutrino coming in and it exchanges a W boson, a muon will come out. So it's flipping within, say, this doublet that you see right here. And if it hits a D quark, it will go to a U quark within the simplest standard model. So it's flipping within the doublet. And so I said something there. I said, you know, if a muon neutrino comes in, a muon actually comes out, okay? And this is an important point because we don't see neutrinos in our detectors. Our detectors only respond to electric charge. And so as a result, we can only see charged particles that are in the detector. And so a neutral particle like a neutrino comes in. For example, the neutrino came into this bubble chamber coming vertically upward. It hits a nucleus at some point and you see the shower of charged particles that are actually coming out. And the way that we know that that was a muon neutrino coming in is because of this doublet structure, that we see a muon coming out. We can recognize that charged particle through the way that we use our detectors. And so that's how we know that it was actually a new mu. So a very important point to this talk that I want you to remember is that we're going to classify the neutrino flavor or type through this charge current interaction. So if an electron comes out, it was an electron neutrino. If it was a muon that comes out, it's a muon neutrino. And I'm not going to talk about them today, but if a tau came out, it would have been a tau neutrino. So that's a little bit too simplified. The standard model we've known for a very long time doesn't have that specific one-to-one correspondence within the quark doublets. We know that usually when you hit a D quark with a W, you get a U quark out. But sometimes we know that you can instead actually get the partner over in one of the other doublets. Most often it'll be the charm quark if you're hitting the D. And the charm decays in a very particular manner so that we know for sure it's a charm quark that actually came out. So actually what we say is that in fact, the flavor state is in fact a mixture of mass eigenstates that we describe through a rotation matrix. So that we're not purely getting out, there's not purely specific doublet partner that comes out in this interaction. The same thing happens in the neutrino sector too. If we create a beam that is all one type of neutrino, for example, here I have pion decay, and pions prefer to decay to muons and muon neutrinos. You can look downstream of this, and in your detector, you may actually see an interaction that looks like an electron neutrino was involved because an electron came out of the interaction. So what that is that is called an appearance experiment. So with an appearance experiment, we start with a certain flavor of neutrinos. We look downstream and we ask, do you see the new flavor? So you want to have the new flavor stick out very clearly in your event sample. You want to build your detector in such a way that you can really see that other flavor. There are also disappearance experiments. You could start with a source which has a certain flavor in it, okay? And it may be 100% of that flavor. And you look downstream and you ask, do I see all of the interactions that I expect coming from that flavor? And if I don't, then what happens is that maybe I had a case where my neutrino went from one type to another type of flavor that I can't see in my detector for one reason or another. One of the reasons might be that that flavor is just too massive in its charged lepton to actually be produced in the charge current interaction. And I want you to remember this idea of appearance experiments and disappearance experiments. So the question is, how is this flavor change coming about? It comes about from a quantum mechanical effect called neutrino oscillations. So effectively, if you start out with a given flavor, later on, it may become a mixture. And in fact, indeed, it may oscillate back if you wait long enough in time so that it becomes that single flavor again. And this can happen over and over again. And neutrino oscillations are just a beautiful and classic quantum mechanics problem. So probably you do this in your junior year quantum mechanics class. And so what you do is you say, for two neutrinos, I'm going to describe a mixing matrix, which connects the flavors to the mass matrix, just as we did with the quarks. And so then I can go ahead and I can write out this in terms of the rotation matrix. And so I end up with these two different states that evolve through time. And you end up, if you then apply the quantum mechanics, with an oscillation formula like the one that I show you right here. And I want to explore that formula a little bit. So this formula, which is the probability that neutrino oscillations will occur in a two neutrino case, so it's a little bit artificial, depends on two experimental parameters. L is the distance from the neutrino source to the detector where you're going to actually see the neutrino interaction, and the other is the energy of the neutrinos. So it comes in as a ratio, L/E, which is effectively a measure of time. Then also there are two fundamental parameters in this picture, and they're going to be important in this talk. One of them is the mass splitting between the two different neutrinos, which I'll describe the masses as bars. So the new 1 here is less massive than the new 2, and the distance between them is describing the mass splitting, which I describe as actually the mass squared. So the delta M squared is the difference between these two. Also, there's this mixing angle that was describing, what is the probability of the mixing between the flavors. And so that's the sine squared 2 theta that will appear in this talk. So if we think about this, then if you think about this formula, if I have a neutrino that has just a single energy, okay, a beam that's monoenergetic neutrinos, which do sometimes happen in nature, although I admit it's very rare, but let's say that it has only a single energy, then I can talk about the distance from the source along this axis, and I can start out with a beam that is purely nu mu flavor. And as I go away from the source, the other flavor will appear, say nu E. And so the amplitude of the probability of this appearing is given by this mixing angle right here. And then it will disappear again. And the wavelength is given by the mass splitting. So here I'm showing you appearance of the nu E, and here I'm showing you disappearance of the nu mu. So the prettiest example of neutrino oscillations, and I guess the point I want to make here is that neutrino oscillations are really oscillations. They're really something coming and going. They're exactly what you think about when you think of oscillations. And if you really want to believe you're seeing neutrino oscillations, you would like to see that wiggle. And the prettiest example of this comes from reactor neutrinos. There's a beautiful example that comes from the Lsd experiment here, which you see the oscillation wiggle really nicely. And here I've plotted it as L/E because now I don't have monoenergetic neutrinos, so it has to go as L/E. Okay, so our world is more complicated than this, but it is a very nice and simple place to start. I need to go to a 3 neutrino model because we know experimentally that there are 3 types of neutrinos, the nu E, the nu mu, and the nu tau. If that's going to be true, then I have 3 flavors. I need to connect them to 3 mass states. And so now I have 3 bars in my diagram that I'm going to use to describe the masses. I am going to have different amounts of flavors mixed in. And I now have 2 separate delta M squareds. I have the big one and I have the small one. And I'm showing you something which is called the normal mass hierarchy, which places the small splitting at the bottom. And we actually know an enormous amount about this model at this point. I think we understand many, many of the parameters in this model very well. In particular, we know that that smallest mass splitting is about 7 times 10 to the minus 5 eV squared, which is an arbitrary number at the moment for you, but I'll talk about other numbers in relation to it in a minute. But I do want to point out to you that the way that we were able to access this delta M squared, we could look at the neutrinos that were coming from the sun, but the problem there is that oscillations were being distorted by matter effects. So I'm going to go back to that beautiful Camland experiment that I was just showing you, which had a distance that was about 200,000 meters, and it had an energy of about 3 MeV. So it had an L over E of about 10 to the 5th. And for this oscillation to be maximized, I need to have delta M squared times L over E being on the order of 1, which was in fact true for that experiment. And that's why you could see it so clearly when I showed you that oscillation wiggle. Now, this one is 7 times 10 to the minus 5. I told you that there are 2 mass splittings. I mentioned that this is the smallest. The next one, the other one that we see, is actually at 10 to the minus 3. So nearly 2 orders of magnitude larger. And this is one where we have been able to do measurements that come also from reactor experiments. We've been able to see oscillations related to it in cosmic ray showers. We see oscillations related to it in accelerator-based experiments also. And so we're able to measure these very, very well, these 2 mass splittings. I want to say, this is an interesting time that we're living in, because really right now, we're at the first year where all of the undergraduates at Case Western were born in an era where people truly believed in neutrino oscillations. So it was really in the late 1990s and the early 2000s that 35 years of data culminated in a set of results that people really felt it was irrefutable. We were definitely seeing neutrino oscillations. And so I feel like we're kind of at an amazing time, because, you know, I was born well before that, and I have lived through those years. And so I've seen that transition, but none of the students will have seen that. And they're all like, yeah, neutrinos oscillate. Why are you making a big deal out of this? But there's some points I do want to make, okay? I want to just remind people that things were not clear in the late 1990s and the early 2000s. There were definitely anomalies out there. We call anomalies something that's on the order of 2 sigma up to 5 sigma. So it hasn't really crossed the threshold of really being a discovery. There were also experiments that had limits. They didn't see neutrino oscillations. And so they were contradicting the signals of the oscillations that were being reported. In retrospect, some of the experiments were seeing oscillations, but were actually suffering from additional unexpected systematics. And that is very confusing when you're trying to understand your data. Also, in retrospect, without physics beyond oscillations, some of the data could not be explained. I mentioned the idea of matter effects for the solar neutrinos. This turned out to be very important. And it is an effect that messes up the oscillation signature if you don't know about it. So theorists had to think of it first. And then lastly, theorists just had very strong views that the data had to be wrong, right? Neutrinos couldn't have mass. I actually had a theorist walk into my office at one point and say to me, you are going to show neutrinos are massless, right? I was like, well, you know, we'll see. We'll see how it goes. And I did not deliver on that. But one thing we can say right now is that we have resolved this with what I think is a truly beautiful 3-neutrino model. At this point, we're trying to understand details of the model, but the big features I think are well understood. Except for some problems, okay? And here is where the elephants come in, all right? So we definitely have some problems within what is going on in our data. So there are data sets that don't fit into this beautiful picture, okay? These are data sets that look, you know, you can fit the data with oscillations, but the problem is that the delta M squared is way too large. If you look at my mass splittings that you see right here, The delta M squared for solar is here. The delta M squared for atmospheric is here. And if I add solar and atmospheric together, I get one more delta M squared that is slightly larger. Remember, this was 10 to the minus 5 and this is 10 to the minus 3. So really the sum is very close to atmospheric delta M squared. And you can't get a delta M squared that's larger. So if I describe that on a plot where I put the mixing angle along the x-axis and the delta M squared along this axis, and those are really the main two parameters of my theory, all of my data from my well-determined model sits down here. And I have a set of experiments at the 2 to 4 sigma level that are sitting with results that are up here at pretty high delta M squared, significantly above where it is that we fit into our 3 neutrino model. And since this is only between the 2 and 4 sigma level, it's not rising to 5 sigma, we call these anomalies. We have two kinds of anomalies, really. We have appearance and we have disappearance. And actually, the disappearance is going to divide into 2 categories. So that's our problem. That is the whole key to this talk. So I'm going to begin by presenting the anomalies as of 1 year ago. And I'm going to go from oldest to youngest. And then I'll talk a little bit about what's happened in the last year. So we actually had anomalies that had essentially 4 different categories, and they came in 4 different sizes. The biggest anomaly at the time was coming from an experiment called Lsd, and the next one was called Microboon. I was on the Microboon experiment. There was the reactor anomalies, and there was also anomalies coming from radioactive sources. So I want to begin with the biggest of the anomalies, and that is appearing in a type of experiment that is the appearance experiment. So remember, in a sea of some type of neutrino, in this case, muon neutrinos, you're looking for a different type of neutrino, in this case, the electron neutrino. So you're building an experiment that will allow you to find that very, very well. And the Lsd anomaly, the way that this was constructed, they used a liquid scintillator detector with a stopped pion beam. So in a stopped pion beam, what happens is that you have most of the pi minuses capturing and also most of the mu minuses capturing. So they're at a very, very low level. So you're only left with this decay chain of the pi pluses, which leads you to have only anti-muon neutrinos. You also have some muon neutrinos here at about 29 MeV, but those muon neutrinos, because a muon is actually very heavy, it cannot interact and produce a muon in your detector. Same with the muon antineutrinos here. So in this, we have no anti-electron neutrinos in this picture. So this is a great place to look to see if your anti-muon neutrinos turn into anti-electron neutrinos. And that's really nice because anti-electron neutrinos produce an interaction that has a coincidence in your detector. First, you see light in a scintillator detector that comes from the positron being produced. And then you see light a little bit later from when your neutron captures. So it goes flash, flash. And you would not have that for electron neutrinos, only for anti-electron neutrinos. So with that experiment, they went out to do the measurement, and what they found was the data that you see right here. And the backgrounds, the in-beam backgrounds are shown here in the red and in the green, and you can see that their data is sitting way above the backgrounds that they predicted. And so that is the anomaly, the Lsd anomaly, and you can fit this excess to oscillations, and it fits up here at this high delta M squared that I was telling you about. So that actually motivated the Microboon experiment that I was on. The idea behind the Microboon experiment is if you go back and you look at this Lsd anomaly, you see that this is actually very low background, but it's also very low statistics. What we wanted to do instead was see if we could get much higher statistics. And we would do that by building a beam line at Fermilab. We would maintain the same L over E, but use larger L and larger E, and we should still access that same delta M squared. And so this was an experiment that ran at Fermilab. It produced pions and kaons that decayed in a beam pipe, and those neutrinos came down and was seen in the detector downstream. Now, this was an experiment that had very high statistics, close to 1 million events. but it had also, unfortunately, relatively high backgrounds. Nevertheless, you can see the backgrounds here in the stacked plot, and you can see the data, and you see that the data is sitting well above the backgrounds that you see right here. And so there is an excess in this also. There seems to be an excess of electron-like events in this beam that was a predominantly nu mu beam. So again, just like Lsd, it's an unexpected appearance. And you can actually put these together. In both cases, you can take that data and convert it into the oscillation probability, the experimentally measured oscillation probability. You can plot that as a function of L over E. You can put them on the same plot, and you discover that there is a model that actually seems to fit the data from Lsd and Microboon together. Okay, so that all seems to fit our oscillation concept. All right, there's a different kind of oscillation out there that I also told you about, and that's the oscillation experiment that's called a disappearance experiment. And in the particular case I want to talk about electron flavor disappearance. In particular, I want to start out by talking about reactor experiments. Reactors are wonderful places to get electron flavor neutrinos. You actually get electron flavor anti-neutrinos. I should be very specific about that, coming out of these reactors. And so you can look for that interaction, and you can ask, do I see as many as I thought that I should? And because reactor power is closely related to the amount of money that a power company makes, they actually know a great deal about the interactions that are happening inside of their reactor. And you can get pretty precise descriptions of the reactor, the interactions going on inside of the reactor, and you can predict the anti-electron neutrino flux from it. And the reactor anti-neutrino anomaly was something that showed up when modern experiments updated the reactor fluxes to reflect this best data that was coming from the power companies. And all of a sudden, instead of lining up with a data divided by prediction of 1, there is a deficit, which is what you would expect if anti-electron neutrinos are disappearing. With that said, I hope you will agree with me, it's got to be hard to actually predict a reactor flux incredibly well. We believe that we understand it, but I don't know. We're seeing some bumps, some strange effects within the reactor fluxes. So as a result, it might be better, instead of looking for the overall deficit from disappearance, to see if you can see a shape as a function of energy of the reactor neutrinos that matches the oscillation prediction. So the example that I show you here comes from an experiment which is called DANCE, for example. So this is their data. And what they did was they took their detector and they fixed it so their detector could go up and down. So they spend about 2.7 days down. They have a midpoint actually, and they also have up as their positions. And this is the ratio of down to up. And so this is changing your distance from the reactor core. So it's changing the L in that oscillation formula. And so you would expect to see an oscillation wiggle because of that, if there are neutrino oscillations. And this is what the data looks like. And so you can ask, do you really believe there is an oscillation wiggle here or not? The best fit is actually the red line that I show you right there. This is only a 2 sigma effect. So again, it just passes as an anomaly. And in fact, there are other reactor experiments that have gone out and alternatively to moving the detector around, instead of built long detectors so that you can compare what's going on in the front of the detector to the back of the detector. Prospect is an example of this, and that experiment has not seen an effect at 2 sigma. But this right here that you see is an example of a reactor anomaly. Now, there's another way to look for anti-electron neutrino disappearance. Look for electron flavor disappearance, and that is to use radioactive sources. And these are experiments only for truly crazy people, okay? So the way that you do this is you produce a megacurie source, which is just an insanely hot source. just for everybody out there who is doing junior lab, you know, you're probably using tens of microcurie source, maybe even smaller, just a microcurie source. So this is a megacurie. It is a very, very, very radioactive source. It is so hot that the source, which was sitting here, which these people are standing next to, was actually, and the source is inside of here with a protection around it. This bin was actually hot to the touch because the gammas in there were actually converting and producing thermal energy. So it was a crazy experiment, which was done in Russia. There was also an experiment similar to it that was done in Italy. And the measurements that were made, the actual purpose of this originally was to calibrate the solar neutrino experiments. But when they looked at the measured to the predicted rates, they came out uniformly low. Now, it's low statistics, but nevertheless, the source rates seem to be low compared to the prediction, which they thought that they could do very, very well. And so again, this looked a lot like electron flavor disappearance. But one type of anomaly is actually missing. If I have nu mu going to nu e, and I have nu e disappearance, I should also have nu mu disappearance. And up until last year, there wasn't really a very clear sign, nothing above 2 sigma for nu mu disappearance. Now, before I go on and talk a little bit about what's happened over the last year, I want to try to put what we had already into some perspective. And I do want to point out something that's very important. I just spent a lot of time talking about anomalies, but the fact is we have run a lot of experiments that have also set limits. And that negative space around our elephants really matters in understanding the elephants. So one way to think about it is if I plot L along this y-axis and I plot E along this axis, given this oscillation formula, if the experiment is sitting at the first oscillation maximum, it should all lie along one line. So this is the line of first oscillation maximum. This line right here would be the line of second oscillation maximum for a given delta M squared. And you would expect every experiment lying along those lines to actually see an effect. But that is not perfectly true. While a lot of experiments along the lines see an effect, and many of those that are off the line don't see an effect, there are some on the lines that don't seem to see an effect. Okay, so this negative space matters as we talk about trying to actually put all this together into a model. So this brings me to the point about the model. Is there a model that can explain it all? And my answer to you is that there is a model. It's a little hard to find it, okay? And the reason is because the information that we have is very spotty. We have information from reactors, Microboon, Lsd, Galaxy, and Sage, and so forth. And it reminds me of a poem which goes, "It was 6 men of Indostan, to learning much inclined, who went to see the elephant, although all of them were blind, that each by observation might satisfy his mind." And so each one of these people come up to the elephant, to a different part of the elephant, and feel that part of the elephant, and they come away with a different conclusion. They conclude that the elephant is actually a wall, or a snake, or a spear, or a tree, or a fan, or a rope, depending on what part of the elephant they actually touched. And so it's really hard to get a whole picture of an elephant if you're only seeing the bits and pieces of it like this. But we're going to go ahead and try. And the model that we're going to bring to this picture is what is considered the simplest solution, which, if you have an extra delta M squared, is to add one more neutrino mass state. Because remember, if I had 3 neutrinos, I had 2 independent mass delta M squareds. If I want another delta M squared, I just add an extra mass state and I get my delta M squared that I'm looking for. And so I'm going to add this extra neutrino in, and I'm going to expand my mixing matrix so that my flavor states are mixtures of these mass eigenstates. And it turns out that I can now write down a set of oscillation probabilities for disappearance of electron flavor, disappearance of muon flavor, and also appearance of nu mu to nu e. Now, an important point about this 4th state that we're adding in is that we actually already know how many active neutrinos that we have, active by way of the standard model. That's been measured by the very precise measurements that come from the Z boson decay. So as a result, the data is actually very hard to see on this plot of the Z boson resonance. There's a data point here, 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 and here. And the difference between 4, 3, and 2 neutrinos is quite large. And you see that it does very well in describing the number of neutrinos that are coupling to that Z boson as being very close to 3. So that means that any new light neutrino, lighter than half the Z mass, is going to not be something which cannot have standard model interactions. It cannot couple to the Z boson. And so the word that people came up for this was sterile neutrinos, which I think is really a terrible word. I don't like the name sterile neutrinos at all, but that's the word they came up with. So our fourth flavor is going to be a sterile neutrino. And this is called a 3+1 model because we have the 3 active flavors and the 1 sterile neutrino in it. And as I said, it's going to have electron neutrino disappearance, muon neutrino disappearance, and it's going to have nu mu to nu e appearance. And a question that I often get is, how is it possible to introduce a sterile neutrino that does not interact and have appearance, right? You can have disappearance because your nu e turned into your sterile neutrino. You can have, but how do you, or your nu mu turned into your sterile neutrino, but how do you get this? And the reason is because of the mixing. So our 4 mass states are actually mixtures of the different flavors. And so this 4th mass state that's got a high delta M squared actually has a little bit of active flavor in it. And this tiny little bit of active flavor, which means that the oscillation doesn't happen very often, allows for the transition for nu mu to nu e appearance. And so that's why it is that you can have the Lsd or the mini Boon result in this picture. Okay, so we can go out and we can fit for this. It's something that my group does. So we put all of the data in, all of the anomalies, all of the limits that are relevant, we put it all together in, and we go out and we do a fit. And we discover that, yes, in the mixing angle and the delta M squared, and remember the mixing angle will be different for appearance, nu e disappearance, and nu mu disappearance, but the delta M squared has to always be the same. And you do get a solution, and the solution has a good chi-squared per degree of freedom, a high p-value. And more importantly, if you look at the delta chi-squared between fitting for only 3 neutrinos and for fitting for 3+1, there is a huge improvement. So the delta chi-squared compared to the delta degrees of freedom is 35 for 3. So that's a 5.2 sigma effect, okay? That is big. You might say that's a discovery. So you can ask, why am I not declaring success? And the answer is, yeah, we see this one. We see the nu mu to nu e appearance. That's Lsd and mini Boon. We see the nu e disappearance. That's the reactors and that's the sources. But we haven't seen the nu mu disappearance, at least in the data set that I've shown you so far. And that is actually at high enough mixing that we probably should have seen it. So we're very worried that we haven't seen the nu mu disappearance yet. So where are we? Okay. So where we are at now looks remarkably like where we were at in the early 1990s and the early 2000s. One thing about neutrino physics is that history repeats itself over and over again. So there are definitely anomalies. The limits are contradicting signals of oscillations in some cases. Some experiments may be seeing oscillations, but suffering from additional unexpected systematics. And maybe that without physics beyond oscillations, the data cannot be explained. And this is an important one that I'm going to come back to. And the theorists have strong views that the data must be wrong, okay? It has to be a 3 neutrino model. It cannot possibly be anything but a 3 neutrino model. That's what I'm hearing again today. And that was where we were at in April of last year. And the situation is only getting more confusing. So what has happened in the last year? There have been 3 really surprising results that almost but don't quite fit our already stressed out model. Okay, so one of them comes from IceCube and maybe a signature of nu-mu disappearance with a little bit of extra help. One of them comes from an experiment which is called the Boxon experiment, BEST, and it is a nu-E disappearance for sure. And then there is the Microboon experiment. The Microboon experiment, which I was also on along with IceCube, was supposed to be a nu-mu to nu-E appearance search, and it looks for all the world like nu-E disappearance. So the situation is really very confusing. That's all I have to say on that. But let me go through these. So the first one is the IceCube result. And so Marjan Mulai, who is called into this talk, actually is the person who did the analysis that I'm going to tell you about here. The IceCube experiment is located at the South Pole. So it is an experiment where the detectors are located in the Antarctic ice. And so it's looking at neutrinos that are actually traveling through the Earth, coming upward and interacting just below or in the detector. Those neutrinos are coming from atmospheric muons, but they're not your usual atmospheric muon neutrinos that you hear about most of the time. These are very high energy atmospheric muon neutrinos at the TeV scale. And as they travel through the Earth, they may suffer matter effects. It's very similar to the matter effects that were affecting the 3 neutrino oscillations in the sun. If you have a neutrino that is a mixture, say, of 3 active flavors and a sterile flavor, like I show you here, and that's traveling through the Earth and it sees a nucleus, then that nucleus actually represents a potential for forward scattering, but only for the fraction of this that is actually active flavor. The sterile neutrino is blind to that potential. So what happens is that when you put this into the Hamiltonian, instead of getting the nice oscillatory effect out that you get for standard oscillations, you actually get the oscillation wave being messed up. And in fact, what happens is you actually get a resonance at a very specific point that depends on the delta M squared of the 4th mass state. And so Marjan and also another student of mine, Spencer, went out and did analyses related to this. And what was found was that at 93% confidence level, if you just ask, is it oscillations involving a sterile neutrino, you actually get an enclosed allowed region. But that doesn't really rise to the level of what I call an anomaly. I say for something to really be interesting and I want to spend my time looking at it, it needs to be at least 2 sigma. But you can ask, what if something else is going on besides oscillations? Remember that oscillations came about because neutrinos have mass. And once you allow neutrinos to have mass, they can do things that other massive particles can do. And one of the things that they can do is decay. And so that's actually what Marjan looked at. She looked at 3 + 1 + decay. And in that case, you actually get a region which is actually much more significant. The data much prefers that. And you end up with about a 97.5% confidence level for that result. So now you are actually at the level of an anomaly. And this is the first anomaly that we have really seen in the muon neutrino flavor. Now I have to say, and I have never said this to Marjan, so I'll just tell her this right now. She actually put up her paper on April 1, on April Fool's. And so I have to say to people, no, it was not an April Fool's joke. It is real. So from now on, Marjan, you have to put your paper up on a different date. Oops. Oh, I forgot that my thing did this. Yeah. So you're seeing neutrinos come, and there's the detector right there. So just showing the neutrinos coming through the Earth. Okay. So that's the first result out there that is a little different from what it was that we had thought we were looking at. Now with that one, with the IceCube, we think it looks like there's oscillations involved, but there could also be decay involved. So the second one that looks a bit strange was the BEST experiment. So the BEST experiment is a 3.4 megacurie chromium source. And it's designed differently from the original source experiments in that this is a more powerful source. And also the detector was built with an inner region and an outer region. So the source goes down into the detector and there's a separated inner detector and an outer detector. These are low energy neutrinos. And so what happens is that you get an interaction which produces an isotope that you then extract out of the detector. And with that, you measure the rate of the charge current interaction. So you can measure the rates in the inner detector and you can measure the rates in the outer detector. You expect your event rate to drop off with time because that is your source dying away. But this is something where they really understand the source. They understand what rate of electron flavor neutrinos should be coming from the source. And the prediction is indicated by the blue line right here. When you compare data to that prediction, what happens is that the data is actually sitting much lower. So the red line is the best fit to the data, and the blue line is what was actually expected. You can see the size of the errors, and you can see that the separation is quite large. This is an enormous signal. It is a much larger signal than anyone expected. And it is consistent with the other source experiments, but remember the other source experiments had very large errors. And so people never even considered that the effect could be quite this large. The disappearance effect could be quite this large. So you can ask, how is it possible that past electron flavored disappearance experiments could have missed this if this is real, especially the reactor experiments? And so people have been thinking a lot about what we mean when we talk about neutrino oscillations. And it has been recently pointed out that the way we calculate our oscillation probability is to assume a point source. But in fact, a nucleus has a fairly large spatial extent, which can actually smear out your oscillation signal through quantum mechanical effects. So you end up with, instead of having the usual oscillatory signal as a function of energy, so energy along this axis, pink is the usual oscillatory signal, you end up with an effect that actually, for a lot of the region, just flattens out. It flatlines. And this is appearing if you are at a fairly far different distance from the source. It's a decoherence effect. If this were true, the reactor experiments would miss the signal and BEST would actually see it. So again, it's the idea that you are bringing in new physics. In this particular case, it's not beyond standard model physics into the picture to try to explain what's going on. Lastly, there's the Microboon experiment. So Microboon was meant to be investigating the mini Boon excess. It sits in the same beamline as the mini Boon experiment. It was looking for nu mu goes to nu e appearance, and it was using a state-of-the-art detector, which was called a liquid argon time projection chamber. These detectors make beautiful pictures. This is an event display of an electron neutrino interaction. So you see the electron coming out and you see the proton that was struck in the interaction coming out. It really is a type of detector where you can see a lot about what's going on in the event. It is also a state-of-the-art detector. And so what was found in Microboon is not what was expected. It looks like Microboon sees nu e disappearance rather than nu mu to nu e appearance. So if you look at the data that came out of Microboon, where the predicted background is in red, the predicted nu e signal that comes from just intrinsic nu e's in the beam that come from decays of, for example, kaons and other things in the beam line, and you looked at the measured values, which are the black, you see that the black points lie low compared to the green. And actually, it's been pointed out that it seems to fit pretty well to a neutrino oscillation signal. With that said, I think you have to be very careful with this one because I'm on Microboon, and I want to point out that Microboon has not published a 3+1 analysis of the data. Microboon published the electron neutrino rates. We observed that we made the statement that no excess was observed, but the experiment has not yet commented on this deficit. And so you need to wait for a microboon analysis that is actually coming. But I will say that that seems to be a pretty solid deficit. And we are trying very hard to understand it. And, we don't know what it comes from, including the fact that this is a state-of-the-art detector. So we have to worry a little bit about that. Okay. So that is a pretty confusing situation. I hope you see that. And we can invent models that will explain all the old and new results together. But I want to tell you a story that a friend recently sent me. The story goes like this. At a turning point in Freeman Dyson's life, there was a meeting in the spring of 1953 when Enrico Fermi criticized the complexity of Dyson's model by quoting Johnny von Neumann. With 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. In fact, a set of theorists with nothing better to do actually managed to do this. They figured out how to draw an elephant with 4 complex parameters and then add a 5th parameter that makes his nose wiggle. So you might want to go and look this up if you want. But the point is, we really have to be careful with all of this data, how we put it together and how it drives what we think about what is going on. So we can invent models to explain all the old and new results, but we really need to be much more thoughtful about the next experiment that we want to do. I think we need to live in an era where things are much more decisive in terms of the experimental results and much less prescriptive in terms of the theory. So we want an experiment that has very high statistics so that we're not exploring the margins of potential signals. We want to use a very well understood source, detector, and interaction. And we want to be able to trace the oscillation wave so that we don't have to assume anything about the theory. We just look at how it wiggles and we understand whether it's just oscillations or whether it's 3 + 1 + decay or something like that. And I'm working on an experiment which is able to do this, and I'm very excited about it. So I want to end by talking to you a little bit about this experiment. This experiment is called ISODAR at YIMI and it has a design with high statistics, a well understood flux and energy distribution, and excellent energy and position reconstruction capability, and a very well understood detector. And before I even show you the experiment, I just want to brag at how beautifully it can actually map out different oscillation waves. So this, for example, is the oscillation wave if you just have standard neutrino oscillations. This is an example of oscillations where you actually have 2 sterile neutrinos, not just 1. And this is an example of the oscillation you would expect with a 3 + 1 + decay model. And you can just look at the data and see the difference. You're not trying to piece different pieces together and figure out what's going on. The data speaks to you right away. So how does this work? ISODAR uses the lithium-8 isotope, which is an isotope that has a very well understood spectrum. And so what we do is we have to produce this because it actually has a very short half-life of only a little bit less than 1 second. So we have to have protons come in. They produce neutrons in a beryllium target that then get captured in a lithium-7 sleeve, producing the flux. And then we use a big detector with 3 protons in it. In fact, the one that we're going to use is probably going to be an oil-based detector. It's called the Lsc Detector, and we expect 2 million events in 5 years. So I am particularly interested in this source. It's what I have really been working hard on. We have actually developed a new state-of-the-art cyclotron in order to be able to actually produce a small accelerator, compact enough that it can actually go in an underground experiment next to a very, very big detector and drive our beam, producing our anti-electron neutrinos. The new underground laboratory where we are going to go is in Korea. In fact, the areas right here are completely finished and ready for experiments. The magenta and yellow areas are under construction, but the construction is actually very nearly finished at this point. So this is what it would look like underground. Here's the Lsc detector that the Koreans are going to build. Here is the ISODAR source, which we are hoping to bring. So here's the cyclotron. Here is the target area where the lithium is sitting so that you can produce your lithium-8 and send your neutrinos into this detector. And I'm very excited to say that the excavation has been going on. It went on over Christmas, so I'm like the only person in the world that wanted rocks in her stocking for Christmas. I was so happy about this. And the excavation is now complete. They're working now on finishing all of the halls, but all of this is actually completely done. And what will we find? Well, I can't tell you, and that's the point of the experiment, right? I don't need to set up this experiment for a particular type of model. I just set up the experiment, and whatever the model is, I will be able to see what's going on. So here, for example, again, is our nice oscillation model, just standard 3+1 oscillations. Here is a case where we actually have that decoherence effect that I was telling you about. That might be because nuclei have a width to them. Here's an example if we had very fast oscillations, how well we would actually be able to reconstruct those fast oscillations. Here's another example of 3+1 plus decay, where the decay is actually dominating. So I'm hoping maybe one of these is right, or maybe it's something more exotic than that. I don't know, actually. But returning to the blind scientists and the elephant, you know, these men from Hindustan, they disputed loud and long, each in his own opinion, exceeding stiff and strong, though each was partly in the right and all were in the wrong. And that's my guess as to where we are right now, okay? All of us have different opinions about all of this data, but I'm guessing that each of us is partly in the right and also partly in the wrong. Instead of arguing, what I want to do is decisively test it with an experiment like ISIDAR. And I want to end by saying that I don't know what we'll find, but with neutrinos, whatever we find is never quite as expected. So thank you very much. And I would be really happy to answer any questions.
Thank you.
Thank you.
All right. So do we have any questions from students first?
Yeah, Yuha?
Thanks for the nice talk. So my question is there a possibility for another charged lepton associated with this sterile neutrino, if it's true?
So you're asking, is there a fourth generation? And the fourth generation space is pretty highly limited because a charged particle associated with the sterile neutrino would probably show up at colliders. So whatever it is, it's got to be more massive than that. And you have to be careful to not allow it to appear in loop diagrams in experiments like G-2 and experiments like that. So there's a lot of limits on fourth generation. So instead of imagining that there is this sterile neutrino with its charged partner, people think of these sterile neutrinos as probably being partners to each of the doublets. And so actually, it's pretty artificial to imagine that there's only one sterile neutrino. There's probably, everything comes in threes. I mean, if it's out there, I would guess it would be in threes. And actually, we only have enough data to fit for up to 2 sterile neutrinos, which is why I showed you a 3+2 model. Because once you get to 3+3 models, there's so many parameters in the picture that you just don't get any improvement from going ahead from a 3+2 to a 3+3 fit. Does that make sense?
Yeah.
That was a good question. That was a very good question.
Thank you.
Yeah, Pavel?
Hi. I want to make sure that there are no questions from students. Maybe Samantha, let me wait for, we like to wait for the
There's
students.
some other students here.
Yeah, I see Samantha and Asher. So Samantha?
Yeah, so my question is that, like, what was the motivation to consider the fourth type of, like, the sterile neutrino? Like, why I'm kind of considering, like, there's another one and considering the rotation, like the mixing of that.
Right. This is an entirely experimentally driven field. So there was very little theoretical impetus to look for a light sterile neutrino. People were interested in a very heavy sterile neutrino. That fits into some unified theories, but a light sterile neutrino, one in the EV range, was not something that theorists expected at all. And so it came out of the fact that LSD, they could not get rid of the LSD result. So LSD brought out its result. It didn't fit in with anything. There was a lot of controversy over it. And so they actually invited a set of people to come in and analyze their data. They just opened up their data set to other people. And those people couldn't figure out what was wrong either. And at that point in time, people started taking it more seriously. And so that was when Mini-Boon was proposed to see if, okay, if it's oscillations, it should, if we keep the L over E the same, then we should get the same result. And so that was why Mini-Boon started up. And then while Mini-Boon was going, that was when the Reactor Experiments suddenly realized they had a problem. They had actually a deficit that they were not expecting. And so that's where the whole thing sort of grew out of. But this is a very experimentally driven field. And I'm a very experimentally driven person, I have to admit. So I am more interested in pursuing anomalies than I am in pursuing a theory, because I think, you know, the world doesn't do what it is that we expect it to do. So I hope that answered the question.
Yeah, okay, thank you.
Sure.
Thank you for the
Sure. Asher?
Yeah, hi. Great talk. Thank you so much. And I hope this isn't too much of an open-ended question, but what are the sort of, I mean, I guess you just mentioned that you're more interested in like observation and theory, but I guess just what I'm interested in is what does all this mean? Like when we find all these different kinds of neutrino things, like what does this mean about the unit? Like you said, the standard model says that neutrinos have no mass. We found that, oh, no, there's a little bit of mass.
Mm-hmm.
And how much does that change? Like how different does the universe look if neutrino, like, this might be too much of an open-ended question, but what does all this mean in the grand scheme of things and in the grand scheme of physics?
So I'm going to answer in the grand scheme of two things, okay? I'm going to answer in the grand scheme of particle physics and then in the grand scheme of astrophysics and cosmology, okay? So in the grand scheme of particle physics, we have an embarrassing model, okay? The reason why we have a model, a standard model and not a standard theory, is because we do not understand where all the parameters are coming from. And even worse, we can turn it into a periodic table. And when you're looking at something that looks like a periodic table, that motivates you to believe that there is something going on underneath. But we haven't been able to put together all of the pieces of what is going on underneath to be able to get to the unified theory that we believe is underneath there, which is very similar to what happened with the periodic table. We had to keep trying to find pieces, and the pieces didn't necessarily fit together the way that we actually expected. So this is actually a very interesting point in what happens if we find that there are these sterile neutrinos, and how do we actually fit them into our overall theories. And so it's a clue in that direction. And so that's the impact on particle physics. On astrophysics and cosmology, there's a very interesting effect, okay? Because cosmology in particular can go out and can fit a set of parameters, which is the standard cosmological model, and get reasonably good fits. Up until a few years ago, the fits were fantastic. And now we've ended up with a problem with the Hubble constant. But there isn't a lot of space within that for what it is that we are seeing. On the other hand, if we're seeing something and it is real, it is real. And so cosmology is going to have to adjust to address this. And so it has a very big impact, I think, on cosmology, if it turns out to actually be what's going on. And so we'll have to understand that. It also impacts astrophysics because it does affect supernova. In fact, sterile neutrinos tend to help supernova explode for various reasons. And other places, it appears in astrophysics also. So the nice thing about neutrino physics is that it actually sits on the borders and you can play around the borders. It's very rewarding that way. I think the students here are great at asking questions. Are there more students? Not that I don't want to answer Pavel's question, but this is fantastic. I've never had that many questions from students.
We have good students. Thank you.
They are great. They really are good. Okay, Pavel.
Okay, thank you so much for this beautiful colloquium. I have several questions, but let me try to make a priority. You know, in the beginning, you say, if I take seriously these anomalies, the 4 experiments, right? LSD, mini Boon, the reactor anomaly, and the crazy one. You say that you can fit everything with a delta m squared for around 1 eV, right? Now, before we go beyond the classical picture for oscillation, you know very well this experiment. Then I always wonder what is the problem that could have this experiment? Because, for example, the reactor anomaly is I don't know if we can call this a anomaly because the deviations are not so large. Then maybe Lsd and mini Boon are the most let's say serious anomalies. But when you go, for example, to Lsd, no, to mini Boon, for example, I remember that in order to predict the background, you had to worry about the delta decays and all these things. And I believe this has been, the experimentalists try to measure all this background. And my question is, before you make the conclusion that you need a 4 neutrino, what can be wrong? You know, I'm a theoretician, then I have to ask this question. What can be wrong? What can we wrong in these 2 experiments? I mean, I want your professional opinion. This is, I think you have the right approach. I need better experiments to do a better job. But if I ask you, what is your opinion? What could be wrong there that they are not able to really make a strong statement? That is the first question I have.
Okay, I 100% agree with you on that. So the first question that we have to ask is what's going on with these other experiments. Oops, let me try to bring this back. Hold on 1 second. Let me find my slides again. There they are. Share screen. So we'll talk about mini Boon first. Mini Boon is easier to criticize than Lsd, it turns out.
Because there is a lot of nuclear physics in the game.
Right, there is. There's a lot of nuclear physics in it. So the trick on mini Boon is to not need to use the nuclear physics models, but instead be able to make a measurement of the rate of the effect.
Right.
So let me give you an example here. Okay, what you're worried about when you talk about the resonances is the production of the pi knots. So you see here a pi knot. Oh, am I showing my screen? Are you seeing it?
Yes.
Okay. So in a Cherenkov detector, you're looking at rings, and an electron ring looks kind of fuzzy, like the one you see right here. And 2 electromagnetic showers will produce 2 fuzzy rings like you see right here. And so this is what a pi knot looks like. And you're trying to distinguish your pi knots from your electrons. So it turns out that the pi knots, most of the time, they produce 2 photons that convert in the detector. Sometimes they do not. And when they do not, it's because either the photon left the detector, which means that you have to understand your conversion length very well, but you can measure that in the detector. Or what can happen is that you can have a decay that's back to back, but it's aligned along the boost, right? So you get one bright ring in the front and you get a weak ring in the back. But again, that's all kinematics. And so you can actually work out how much is in that region that you were not able to reconstruct using the 2 ring events that you were able to reconstruct. So rather than use any kind of theory in order to constrain the backgrounds, what we do is we use the data. So what you see in this plot is you actually see all of our stacked backgrounds, and you will notice that there's these little crosses right here. You see a cross here and a cross here. See these little crosses? I don't know if you can see them. They're low and they're on, but they're not perfectly aligned with the bars. So the bars are the original theory prediction, And then the crosses are what you get when you constrain our backgrounds using tricks like what I just told you. So it doesn't lead to a very large change, partly because we tuned the theory to try to make it match right before we started out. But we use the data itself in order to, of the events that we actually reconstruct, rather than using a first principles prediction. So that, though, your statement that there are large backgrounds in Miniboon is not one I will argue with. I completely agree with you. There are large backgrounds in Miniboon. And part of the reason why I really like the Lsd experiment is because it doesn't have those very large backgrounds. So we don't have to contend with them. And I'm very worried about what those large backgrounds mean. Now, on the other hand, there's the Lsd experiment. And the Lsd experiment is a very hard one to get around. This particular stopped pion beam is a beautiful beam to have. And so you have to somehow come up with a background which is going to produce anti-electron neutrinos in your beam. And that is much harder to do. And you end up with a case where, although the backgrounds are very small compared to the excess that they see. Now, what you would want in this experiment, if you were to redo it again, is you would really want to run for longer, right? Or have a more powerful beam. And there are a set of experiments out there that are trying to get to there. There's JSNS squared in Japan, which is trying to actually do that. But unfortunately, they haven't been able to get the funding to build a large enough detector yet. So I worry that all of these detectors are sort of sitting at the edges of what could possibly be going on. So, you know, you're right. We have maybe, I guess it's 8 or 9 experiments with anomalies, okay? All 8 or 9 experiments could have something separately wrong with them. You're absolutely right. And it could be that then you bring it all together and you end up with, unluckily, having all those things that are wrong add up. And that is definitely an outcome that could happen.
Sorry. Now, the second question is this beautiful IceQ result. You say that you can do the fitting with the decays as well. But my question is that assuming also a very large delta M square around 1 eV plus decay, you can fit everything well?
Yes, it turns out that it's about, I think it's 4 eV squared. Is Marjan still on? It was like 6.6. Oh, 6.6 eV squared. So, you know, I should say around 1 eV, that's kind of a fuzzy number, right? You know, we're trying to narrow it down, but 1 and 6, it all agrees. There's a big allowed region for it.
Thank you.
Thank you. Stacy?
Hi, thanks. It's very interesting. So I want to explore a little deeper on the cosmological implications now that Pavel has asked the obligatory theory question that the experiments are wrong.
That's all right. I'm not going to.
Well, so let's just say they're right, and there is some kind of extra neutrino with mass. Now, conventionally, I understand the number density of the 3 normal neutrinos from the thermal evolution of the early universe. And hence, we have a limit on their mass density from structure formation theory, which seems like it would be in big danger if there is this extra neutrino that's massive. But I don't understand the production mechanism. So how many are there, and how does this impact the structure formation story?
Right. So you have to play some games with it. Okay. So one of them is that, of course, if they actually are mass states that decay, they go away. So that's one of the nice things about the decay model. But another is that you can set it up so that what happens is that they freeze out early on. You can set up a CP violating system where they end up freezing out early on in the analysis. I actually have taken the point of view of not arguing with the cosmologists. My only statement is this: if these anomalies remain, they need to think of a new theory. That's like,
I actually can have made a comment. There are two solutions to this, and I totally agree with Janet. This is the right attitude because we don't know how they are thermalized. The contribution to N effective depends a lot on at what temperature they're thermalized. This is point one. And there is a second solution when delta M squared is so large, you can have a large lepton asymmetry in the universe that actually help to have a consistent picture. There is a contradiction with the baryon asymmetry because it's a small, but there are actually scenarios where you can do that. Then even if you have a delta M squared large, you can play these theoretical games to have consistent scenario that you don't mess with N effective. And it's actually consistent. It's actually possible.
I imagine there will be even more solutions if in fact this turns out to exist.
Almost certainly. I mean, because there's two issues, right? There's constraining ineffective, which, yeah, I don't think you can mess with. But there's also the limit from structure formation, which the sum of the three neutrinos has to stay under 0.12 eV. That's really tight. And so that
is how you do, because again, the N effective, the contribution of the N effective depends on what temperature they decouple.
Sure.
And therefore, this is how you can actually show. This can be done. It's actually not very hard, to be honest.
Well, it's an important
numbers are all
constraint.
correlated. I mean, I think the problem is that the numbers end up highly correlated.
Right.
And when you extract one number, you're looking at the diagonals of the error matrix, but you don't understand the correlations that get hidden in the matrix.
I don't know if we can ask more questions, but maybe the students, I don't know.
Yeah, maybe we should turn off the recording and end the formal part of this. And
Sure, but I'm glad to see
again.
the talk. This is really fun. This has been a very fun colloquium to give. Thank you so much for all these questions.
Yes, thank you.
But
It was great.
yeah, we can continue afterwards with off the record questions.
Okay.